Thank you so much for taking your time to join this very exciting call on Tech in Depth. And today, I would like to understand your perspective on a very important vertical called cement. So let me begin my conversation by saying how important and how critical is cement as an industry in terms of production and in the ecosystem, and what is the most critical application, the heart of it, which is the most toughest application that is typically from the technology point of view, where people end up spending most of their time.
Sure. See, I think cement is obviously one of the most important indicators of infrastructure growth, because cement drives infrastructure in a big way. And cement is a growing industry, as we are all aware, right? It's been growing across most of the regions. And the most critical aspect in a cement process is the kiln and the mill, right? So the kiln and the VRM, which is typically the most common form or the most recent form of milling that is used, because it's much more energy efficient than the traditionally used ball mills. I think these are the two most critical parts of the cement process.
For those who are uninformed, VRM stands for?
VRM is nothing but a vertical rolling mill, right? I mean, it still does the same job of a mill, which is grinding. Think of it as a very big grinder. Grinding elements, these rollers, which actually use on top of a grinding table, they actually grind any material into smaller particles. And then in VRMs, the way it works is you also have the classifier integrated on the top of the grinding section, separator or classifier, and the coarse and the fine particles are actually separated through that, which is then taken through the separator. This ensures, and VRM, by design and by structure, is much more energy efficient than other forms of grinding, and that is why more and more we see VRMs being used in a lot of cement industries because of its better energy efficiency.
So in terms of vertical roller mill and its complexity, what is it that makes it a difficult to operate and manage application?
So VRM, because it's integrated, right, and you have the classifier and the grinding together, right, in the single structure, it becomes extremely efficient. At the same time, it becomes very critical, right? I mean, it has more points of failure, which means even if there's a problem in the classifier, in the gas flow, which is used for drying, or the main drive, or the grinding process itself, even if the grinding table is unbalanced, it results in problems. So the VRM is important to be maintained in the most optimal way possible to get the best optimal results as efficiently as possible. Just because it's an integrated system, it has more failure modes, which means you have to do much more to ensure that the VRM is delivering the best results optimally. But if you do that, you can get amazing results.
I think that's a perfect segue to now go towards what is the journey that is a recommended journey from maintenance perspective and production engineer perspective. What is it that is the recommended journey that they go through to make sure that they don't have unplanned downtime and the best efficiency and productivity out of that particular equipment?
Definitely, I think it all starts from a foundation of a very strong FMEA, right? Both from an equipment as well as from a process standpoint. And really understanding what are the different failure modes for the VRM, and ensuring that you are able to accurately define the severity of the failure modes, the occurrence of the failure modes, both from past as well as from global knowledge bases, right? Because what has happened in the past may not be what will happen in the future in a lot of the failure modes. So being able to bring in both the global knowledge as well as the local knowledge for that particular equipment or site, and actually taking them into consideration to have a very strong FMEA, which is the foundation to actually define what needs to be monitored, at what frequency, how often, with what accuracy, and with what intensity. That becomes the foundation. And then obviously, basis that you can get into actually defining what type of technologies you want to use to ensure that there is a very high efficiency in terms of cement processing. And because the failure modes are higher, I think VRM we have to look at much more depth in terms of technical depth, in terms of the various failure modes, and making sure you're covering all the different combinations of failure modes, complex failure modes, as well as simple failure modes across all the components of the VRM, as well as the process, as well as the quality of the input compared to what you're trying to get as an output.
And typically, this is where the goal setting and the what you just described is possibly the goal setting and baselining. And then in the journey part of it, how is it that people often jump directly to the technology dashboards or otherwise sensing? What is it that they miss in this particular journey that which is the critical success factor of ultimately delivering their expected performance?
Yeah, I think not doing a thorough job on the FMEA is, I think, the basics, right? That's where most of the people fail. If you do a thorough job on the FMEA, if you do a thorough job on the kind of failure modes you're trying to avoid, and then being technically sound in terms of the technology that you're choosing. See, AI, software, all this is great, right? But if you're not having the right sensing elements, if you're not using the right sensing technologies at the right sensing locations, right? If it's not on the load zone of a bearing, for example, if it's not at the right application, not using the delta P properly, right? I mean, no AI or software is going to kind of help the solution, right? So I think the importance of the sensing as a technology, as part of the overall solutioning, is extremely crucial, which is left out by everybody. I think the traditional or the thought process that, we'll have a platform, bring in everything and figure out what to do next, kind of, underestimates the importance and the complexity on the sensing layer, on the sensing technology selection, and the impact of the sensing technology selection on the platform technology that is being chosen, right? I think these are extremely important to be thought through, rather than just completely making them independent, separate, and thinking of them separately. And that's something that we've seen failing in a lot of applications.
In a way, it's very interesting what you're saying. In a way, you're saying that while AI and the accuracy of predictions are important, but if the base data itself is not correct and accurate and doesn't have the right lines of resolution, and all the environmental conditions being handled properly, that is what is also impacting the success of the insight.
Yeah.
But if I ask you to double click and then open out for the viewers, when you say sensing, is it only the sensor, or it is also the metadata of what all the equipment actually is supposed to do? I mean, how can somebody do a good job at selecting the right sensing? What are the things that they should be thinking about?
No, various things, Kalyan, right? I mean, right from sensitivity, resolution, accuracy, temperature, performance, right? Looking at the performance curves across various temperature ranges. For example, the bottom bearing of a separator, in this case, will be running at 110 degrees Celsius. You want to predict a fault in that. You want something that's going to work in that kind of harsh environment, that temperature, internally, right? Which within the enclosure. How do you make sure you're getting the right technology to monitor that? But I've seen so many cases where, we talk to cement manufacturers, and the biggest problem is they had a separator failure because the bottom bearing went kaput. And the bottom bearing will have a lower life because of the environment that bearing is in, right? So it becomes even more important to be able to choose the right technology to monitor that bearing accurately, even more so than the rest of the bearings, which are easier to approach or reach. VRMs have a lot of internal bearings, as you know, both on the gearbox side as well as on the separator bottom bearing side. Some of them are high temperature, some of them are submerged in oil, and you have accessibility challenges to these VRM bearings to be able to diagnose and predict the failure of each of these bearings individually, right? So sensing technology has to be chosen very, very mindfully, very, very accurately. There's something called resonance, right? Frequencies for the various sensors that are being used. Those have to be chosen accurately. You have a lot of slow speed applications, right? So the gearbox output could be as low as 20 RPM or even lower, right? In some cases. How do you make sure that you're considering the sensitivity required for that kind of an application, and ensuring that you have the right technology used for predicting faults in those kind of applications. So I think when you go to the FME, I think each of these has to be a separate failure mode. You can't just say, oh, bearing failure is a failure mode. No, bearing failure is too broad, right? The bottom bearing of a separator is different from the top bearing of separator. So that's the level of depth that needs to be looked at. And when you go to that kind of granularity and depth, and the kind of detectability that you require to reduce the risk of that component failing, the technology selection also changes for each of these components. So it's not a one size fits all, right? For example, if you don't have the delta P for the VRM, right, you're not going to be able to predict a lot of failures that happen in the VRM. Same way, if you don't monitor the bottom bearing of separator, right, you're open to a high level of risk while you might be covering other points. So you have to look at the entire equipment as a whole, a thorough FMEA right down to each component, understand the environment of each component, and then look at detectability and technology for detectability per component to ensure that you're covering all the failure modes, and hence have the right selection, right, of sensing technology, keeping in mind how the detection is going to happen, right? So you cannot choose sensors independent of the knowledge of how you're going to predict the fault. You can't have a predictive algorithm without the knowledge of what sensing technology is going to be used to predict the fault. Both are important. Both have to go together, right? One without the other is a recipe for a disaster. Yes, it might still work in some conditions. I'm not saying it won't. But in applications like VRMs, you have to think of both together, right? And make sure only then you will be successful because you've considered both aspects.
Okay, very interesting. So that means a bearing is not a bearing as long as it is in dynamic separator bottom bearing. You're saying that it's not all bearings are the same, and you need to really understand what is the contextualized part. That's a very interesting pointer. Okay, now if we move from advanced sensing technology towards, I will take the focus to agreed. We have done a great job. The users, whether it is a production engineer or a maintenance engineer, has followed all the steps that you have just described, and then arrived at a good sensing technology. Now let's come to the predictability part of it. How easily can they arrive at a prescription? And I'm choosing prescription on purpose and not prediction, because while it can predict the accuracy, and I should be also able to understand what is it that you want me to do to avoid that particular scenario, and henceforth in that context I'm using prescription. If the ease of prescription, what are the top 3 things that they should keep in mind to be able to select the right technology for ease of prescription?
So you're getting into the algorithm side of things, right? So prescription obviously has to understand the physical aspects of the equipment. See, a lot of times what we've seen is there are a lot of these what we call ML models or predictive models, right? Which just says, put in data, you'll get an output. Yes, you put in data, you'll get an output, no doubt about it. How much of it is really prescriptive in nature in terms of physical accuracy, right? See, there are a lot of things that will change. A model will not give the same outcome, or the output of the model will not be relevant if, for example, you don't know whether there's a forced lubrication or a splash lubrication, right? So if you don't know the type of lubrication being used, right? Let's say there's a vibro pad versus there's a concrete foundation versus its installation is on let's say a small steel structure on the ground, right? All of these 3 cases, the algorithms have to change based on that. You can't use the same algorithms, right? The coupling, very important, right? Different types of couplings require different types of analysis techniques, right? The predictive algorithms have to change based on. There are lots of inputs like this. I just gave you a bunch of examples, but there are a lot of inputs that are needed to be able to give an accurate prescription in terms of what's actually happening. Because when you're prescribing something, you're also giving an actionable, right? You're saying this is what you need to do. It's not about saying this is the fault. When you're saying this is what you need to do, which means you're assessing multiple things. You're assessing the fault, you're classifying the fault and saying, okay, this is the specific fault. You're also classifying the severity of the fault, right? Because at different severities, you will prescribe different actions. You're not going to give the same action if the fault is of low severity. But if the fault is high severity, you might ask the user to actually stop the machine and just change the bearing. Whereas if it's of a low severity, you might just ask for lubrication, right? So you're assessing the fault, you're assessing the severity of the fault, you're assessing the action based on these two plus the physical condition of the equipment, right? Like I said, what's the mounting condition? What's the coupling? What's the type of lubrication used, right? Imagine if there's a continuous lubrication, right, forced lubrication system, and you say, go lubricate the bearing. What do you think the kind of trust you're going to get into the system, right? It doesn't make any sense, right? I mean, the users are not going to think about, oh, what's the AI model getting as an input? They're just going to say, hey, this is stupid, it doesn't work. So there are a lot of physical aspects, or what we call config data in some sense, right, which is needed to give the right prescriptions.
Contextualization.
Yeah, but the models should also be trained on all these various parameters, right? The same VRM or the same equipment with different physical conditions will have different patterns in the fault signatures, and that has to be trained. So I think the point is that, loosely saying, hey, there's a predictive algorithm, you give me data, I'll give you outputs, is nice to say, right? But when you actually get to accuracy of prescriptions, is it coming at the right time? Am I getting exactly the right recommended action, which is optimized for me, right? I can't be replacing a bearing every time there's even the slightest change in pattern, right? I mean, then my bearing cost is going to go up, and I can't keep changing my gearbox, right? Every time you see a small gear mesh, issue, I'm not going to change the gearbox every time, right? Even if you have the slightest lack of confidence, because see, these are physical systems, dynamic in nature. There's also God's forces. So even if you have the slightest doubt, are you going to ask me to open up a cement mill gearbox, right? And what if it's false? What is the impact of the FP versus, taking a chance on that? There are so many considerations that the model has to take, just like, today's AI goes through the thinking process, right? I mean, what are we doing? We're looking at various different optimizations in terms of what is the risk and reward for taking a certain action. And you're presenting the most optimum action, taking into consideration the loss functions, the risks and the rewards, right? So that's,
Very
I think, where the crux lies, and finally, look, who's going to adopt this? Who's going to use it, right? They need to feel whether this is worth it or not. They will be the ones giving the feedback on the accuracy or the importance or the usefulness of the recommended actions, build trust and adopt and create value, right? And if that doesn't work, you could do whatever you want to do, right? It's not going to work.
Okay, just to summarize what you have just explained over there, they need to look at not only a prediction, which in most of the cases they might be looking at things like, can you check this, can you check that, can you check that? This is more throwing a dart in the dark and then giving multiple things because it is not really pinpointed. So the place where they have to be very careful is what is the time, effort and the value that they actually are going to end up spending on those predictions. And henceforth, the lesser they get, the more accurate they turned out to be, which is where I pick up the word validation that you used. So this is in a nutshell, the more precise the prescription is and the higher validation rate that it has, that's a place where the user should be focusing on, instead of looking at the English part of it, that everything is a predictive AI and then prescriptive AI.
Yep.
Now, if I actually move to the value side of it, that's a very interesting point that you touched on in terms of value delivery. What is it that is the gap that is currently in the market? Typically, me as a maintenance engineer, I'm actually looking at everybody saying that, this is 99 point plus or 95 plus, 98 plus. I mean, the numbers are, I'm so sorry to say this, but seemingly same. So how is it that for me as a value, what is the tip and what are the top 3 things that I should be looking for to be able to figure out what is the truth and what is not completely true?
See, that's not easy, right? I mean, there's I mean, information is available to everybody.
Correct.
Very easy to get to half knowledge, 3/4 of knowledge, right? Few questions to AI models, and anybody can become seemingly an expert in cement. See, I think what is critical for anyone to be successful in this is to be able to connect all the dots, right? From FMEA to sensing technology selection to predictive algorithm training, linked to the right technology selection, trained on the right applications, trained on actual physical attributes which physically exist in the system, right? Making sure that is coming in, having enough amount of training across various types of such physical attribute combinations to be able to give the right prescription, which is validated by users, right? I mean, this whole cycle, if you think about it, it's everything has nuances, right? Right from where you install your sensor, right? Where do you install your pressure sensor? Where do you install the vibration sensor, right? A bearing has a load zone and a dead zone. If you install it at the dead zone, that too in a slow speed equipment, right? Guess what? You're not going to catch a fault. How do you make sure that it's in the load zone, right? If it's not exactly in the load zone, let's say it's at 30 degrees off from the load zone, what happens then when that happens? Because you cannot always have it on the load zone. Your load zone, sometimes it may not be possible to install in the load zone, right? So then you are taking a bit of a compromise there. How does the platform know that, right? Everything, such simple, I'm just talking about little nuances, right? Very small things, but they will impact your output. So, and then, when something doesn't work, getting into the root cause analysis to figure out, what was it that actually, why it didn't work, right? Is it the sense of the location? Is it the position? Is it the selection? Should I gone with a MEMS technology, piece of technology? What sensitivity? What resolution? What fmax? What kind of accuracies? How much in the high frequency? How much in the low? See, every time high frequency is not good. I've seen so many companies using very high just to say, okay, I get the more frequency is better for me. It's not always good. And we can go into that some other day as to why that's not always good. But, I think, all of these aspects are very critical, right? How do you make sure slow speed is accurately predicted? How do you make sure bottom bearing, separator bottom bearing is accurately predicted? How do you make sure gear teeth, gear shift, gear misalignment, backlash, every single fault, right? Failure mode, very, very critical and impacts, and all of these things matter, right? So how do you get all of these dots connected, right? That's the only way you will get accuracy of outcome. Otherwise, you're not going to get accuracy of outcome. You could have the best platform in the world. How does it matter? Best AI in the world. How does it matter? Right? You have to get everything right. Only then it will work.
And imagine my plight that I'm actually seeing most of the times. Me as a maintenance manager, I'm still seeing most of the flyers that I get, whether it is on LinkedIn and in-person presentations or demos. If there is one indicator that I should look for, how can I chaff out what is the truth versus not so complete? I'm sorry, I'm pushing you from top 3 to top 1. What is the most? I am not an AI specialist, but I'm very good in what I do. Now tell me, what is that one?
So Kalyan, I will talk to 5 users. Because see,
okay.
See, let me tell you, only the users know the truth, right? It's very easy to get clouded by a lot of information online, right? Whether it is through AI tools, because they are also finally trained on online data, right? Whatever data is available, that's what they answer, right? So there's a lot of noise out there, right? And everybody will always say they are the best, right? Nobody's going to say they are second best. So I think the point is, how many of these users are validating? How many of the users are actually seeing value? How many of them are actually seeing that the prescribed actions, when I take those actions, actually create value, right? In terms of extended asset life or saving a potential breakdown, right? How many of those am I actually seeing? How many of them can put their hand up and say yes? And it's consistent. It's not a one-off case, right? So you could always have a one-off case, right? I mean, sometimes some faults are pretty obvious, right? It's the subtle ones which are the tough ones. The obvious ones you can even do with offline monitoring or just trending, without even having to go into depth. It's the subtle ones which matter. And those are the ones which make a difference, right? How many users have consistently seen improvement in MTBF by using a tool like this, right? And by consistent, I mean it's like week on week, month on month, quarter on quarter. Yes, this the prescriptions make sense. They're consistent. They are accurate. And yes, everything's not going to be 100%. You're not going to catch every fault. Not every fault you catch is going to be accurately caught. See, everyone gets that, right? But I think where's that consistency proven in actual real customer environment and cement industry? I think that's what would be very, very important.
So how much it is validated and how much it is verifiable, and where is the validation happening, if I may just extend it to the third part? So that is placeware. Is it something that is digitally verifiable? Can I speak to the users? That's what you said, speak to the users. So I think a healthy combination of speaking to the users who have used it, and also digitally, if it's very verifiable, that somebody talking about saved hours, whether that is signed off somewhere. That is what 2 points. That's a good okay, I take these 2 points. Now last, if I zoom out from the technology side of it, we're on top of the time for this conversation. So if we zoom out, I have one last question that is very popular amongst most of the users and operators on site. How much of AI is actually going to really good enough to replace me, or will it replace me?
Look, if you're doing something that's physical in nature, it's not going to replace you. If you're doing something that's not physical in nature, which is repetitive, where the amount of intelligence that you're putting into in terms of value addition is not high, then yes, that will get automated, right? But AI is not going to do anything that's physical. AI is not going to do anything that is highly intellectual, where you're adding, and anything where there's a physical plus a digital combination, right? So AI is going to speed up the process. So AI is going to significantly enhance productivity and efficiency. There's no doubt about that. So for example, something that would take you, let's say you want to do an RCA and there's a problem in the plant, you want to do an RCA, and let's say normally you do the fishbone diagram and you go through Pareto's and you do all that stuff, right? Let's say it takes you 5 hours to do an RCA. I'm just taking 5 hours. Usually it takes much more. AI can make you do it, help you with doing that in like 10 minutes, right? It can get all the information on its own. I'll just give you a simple example. RCA is a great example where AI can massively improve efficiency and productivity, right? Where you have, your top 3 potential root causes right there in front of you, and then your intellectual and your experience and knowledge of the process can kind of narrow down to one, and you can take the necessary corrective actions and recommended actions. But yeah, so is it going to replace? It's going to replace repetitive tasks. It's not going to replace anything that's physical in nature. It's not going to replace anything that's physical plus digital in nature. In fact, it's going to help improve productivity and efficiency, and you can do much more with your time.
Okay. So I take the 3 points. Number 1, if it is repetitive, I can actually do higher value tasks. So that's a good thing. I don't need to be worried about it. Number 2, if I can do some of the things faster, for example, the RCA example, if I can do it faster, maybe that means I can also use this as a assistant to speed up my process. So that is improving my productivity. So I don't need to be threatened in that. The last but certainly the most important point that you said is ultimately it is just accelerating my decisions, but it is not replacing my physical presence.
Absolutely.
Well,
absolutely.
There might be a scenario in dark factories, but not in cement, not today. Okay.
No, so, look, all that is fine. Look, there's always going to be a physical element when there's equipment and machines, and
correct.
You have to replace a bearing. It's all going to have a life. So look, those physical aspects are not going to go away, right? AI is going to really, really help improve decision making, and I think everyone should adopt it. There's no doubt about it. It's not about if, it's a matter of when. We all know that, right? AI is going to come in, but we have to look at it as a tool, just like digital is a tool, just like your worksheets are a tool, right? To note down stuff, right? I mean, everything is a tool. We don't have to look at it as it's bigger than the human, right? It's just a tool.
Thank you, Ronak. That was a very detailed tech in depth about vertical roller mill and cement industry. Maybe next week again we'll meet with another vertical, another application, and then cover this particular tech in depth discussion. Thank you so much for your insights.
Thank you, Kalyan. Really appreciate it. you.